Alright, welcome to another video for AQA AS Chemistry. Today we're going to be doing ozone depletion. So this is going to be, it's quite a short topic, but it can be carried on throughout the rest of chemistry really. Between 1928 to 78, halogen alkanes called CFCs, which are called chlorofluorocarbons, were once widely used in industry. These CFCs often escaped into the atmosphere where they depleted the ozone layer. So CFCs and ozone. The CFC is just a chlorofluorocarbon molecule. Hence, CFCs only contain a carbon, chlorine, and a fluorine atom. Ozone has the formula O3. O3 is significantly less stable than O2. O3 is formed from O2 and UV light. O3 is present in low concentrations in the upper atmosphere. Its highest concentrations are in the ozone layer in the Earth's atmosphere. You have ozone depletion. CFCs can undergo photolysis in the atmosphere. Photolysis is, as it sounds, is broken down by light. Photo meaning light, and lysis meaning to break. So break down using light. And this process creates chlorine radicals, and these chlorine radicals later react with O3. The mechanism for ozone depletion is the structure. So we have three stages of these types of these free radical substitution. It's called free radical substitution first of all, and the mechanism is split into three stages: initiation, propagation, and termination. So the destruction of ozone is a free radical mechanism. So the initial step is, let's get this here, initiation. So I'm just gonna go through this, put it over here. Initiation, so we would have Cl2 that is broken down into two Cl free radicals, and that's fed by UV light. UV light causes that. The propagation step that comes next, so I'm trying to angle this in the right way. The propagation step that comes next is when in the initiation, you're always going to form free radicals, and your reactant side has no free radicals, and your product side will have free radicals only. The propagation step means that you'll have free radicals in both the reactant side and the product side. So if you have, for example, Cl free radical plus an O3, an ozone, and this is how it depletes it. This Cl, this is very, this Cl free radical is very reactive. It doesn't like to be in this position, so it'll react with an oxygen. And it's still, even when it's like this, it still forms a free radical. That's still a free radical plus an O2. So now it's depleted some of the ozone, and it's got you still got this CLO free radical plus O2, and then this CLO free radical can undergo a further propagation step. It's always important to make sure you put the dot here. The dot's actually more to do with the Cl, but it can put on either side, but you got to make sure to put the dot in. It's not a minus, it's not a minus or plus or anything like that. It's always a dot when you're talking about free radicals. And that also reacts with O3, and I formed a Cl free radical again, and then plus 2O2. And this can repeat over and over again. This can start a chain reaction really. The final step is called termination step. The termination step is you have free radicals on your left hand side of your equation, and on your reactant side, and on your product side you'll have your on your product side you'll have no free radicals. So it's the opposite of your initiation step, which makes sense. Termination step, the ending of it. So two Cls, for example, two chloride free radicals can react together to form Cl2. Some of the, now it doesn't always have to go in this step. These are just some of the steps. If it goes, it could just go from here and then back to forming that again. But this is just to show you what steps that take place in a reaction, like in the exam. If you get stuck, they'll give you in the exam. It actually sets up just like this. This is the initiation step. That's the propagation step, and then that's the termination step. And then they'll ask you to fill out the each. They give you a dotted line to write on and tell you to fill it out. So that's probably, this is like just trying to get your understanding of what it's like in exam. It's very easy steps. It's not obviously going to be this example. They give you different examples. It will be a longer hydrocarbon. I mean, the principle still applies, to be honest. If you go for an example, let's say chloromethane, right? So in your initiation step, that would go to forming through obviously UV light. We're forming this radical here plus a Cl radical here. So that chloride radical can react just like this reaction here. So the chloride free radical plus an O3 chlorate, a chlorate free radical here. So chlorate, and then plus an O2. That other one there, that other free radical, can't really see what I'm doing there, but that will react with a Cl2. So you can still have, this can be in the propagation step because it could be free floating in the atmosphere. So that can, just remember what a propagation step is. Free radicals in the reactants and product side. So you can still have this free radical react with, because remember free radicals are very, very reactive. So that can react with the CO2, and you could reform chloromethane, and then form another chloride radical. And then in the termination step, you could have that, so two chlorides, so that's just having that again, so two chloride free radicals forming a Cl2, and then you have your H3C radicals. Like when you're having these reactions, it's gonna be it's usually the two of the same thing happening again. So I just write it like this just so you can see it a bit more clearly, see a bit more clearly what's going on. But those two are just reacting together, and you've now formed an ethene. What do you form ethene? An ethane. Sorry, why did I say ethene? It's not ethene. Ethane. My bad. So why I said ethene, but as you can clearly see, that's going to react together to form an ethane, and that's that. So you have to understand why CFCs are just bad. So the Montreal products, so CFCs were used in aerosols, and they were used in aerosols as coolants in fridges and as solvents in industry. Science collected evidence in the 70s that they were damaging the ozone layer, and they eventually led to bans beginning with Sweden in 1978 and the development of safe alternatives like HFCs. You don't really need to know this, but this is just to give a bit of context. So they're safe nowadays. There are safer alternatives to CFCs to prevent ozone depletion. But why? I think you need to understand why is it so important that we don't have ozone depletion? Like if I asked you, you know, why is it so important that we don't deplete the ozone layer? What's so special about the ozone layer? Why is that, why do we need the ozone layer? And it's important because you try to think here, but I can just do it here anyway, it doesn't matter. Let's have I got image. So I do have the image. Great. So it's taking you back to a little bit of GCSE physics, but you need to understand what these greenhouse gases do. They're good to an extent and bad to an extent, but in terms of, you have high frequency infrared radiation coming from the sun, and some of it passes into the Earth's atmosphere. Some of it gets reflected back out. Some of those greenhouse gases can, so some of it's just reflected in the upper atmosphere, and some of it can pass through. The part of it that passes through, the part that gets reflected back is caused by these greenhouse gases reflecting it back into space. But the part that gets through gets absorbed by the surface of the Earth, and it gets re-emitted as low frequency infrared radiation. And some of that then gets absorbed by that low frequency infrared radiation gets absorbed by greenhouse gases, such as ozone, because ozone is a greenhouse gas, and it gets redistributed in all directions. Greenhouse effect isn't bad so long as it's controlled. If it's under control, then that's going to be a problem. It's going to cause certain areas to be too cool. We need these ozone gases to, and at the same time, it could be the sense that you're not maintaining heat. Also, it's too much heat, because now there's not that ozone layer to protect us from the UV rays from the sun. So you can have very high frequency infrared radiation coming from the sun that's not being reflected back out by ozone layer, or also there's other things just about except for heat, even UV light causing skin cancer and things like that. So the ozone layer is important. It's important to keep the ozone layer, but to an extent. But it's also, so that's why we have to. That's why CFCs have to be banned, because depletion of ozone layer is a serious problem. But that's it really. That's what I can give you for this video. Hopefully it was helpful.